Welcome back to the series on Calculus 1. In the last video, we introduced the concept of integration, and we started talking about taking the area under different curves. We found it was very easy to take the area under the curve of a linear function or a constant function because these just formed simple geometric shapes with the x-axis. And so finding the area under these curves was not very complicated. It was very easy to derive some formula for that. But then we talked about the function y is equal to x squared, and we saw that finding the area under this curve proved to be a little bit more elusive. And the way we went about this was we broke this area up into several different finite rectangles. And the way that we did that is we would break these up into a certain number of rectangles, and then the width of each rectangle would be formed by the length of the interval, which in this case would be, since we're going from 0 to x, would just be x, divided by the number of rectangles that there were. That would form the width of each rectangle. And then the height of each rectangle, in the example that we use, would be the function evaluated at the beginning of each interval. So for example, the height of this rectangle is the function evaluated at the beginning of this interval. And what that winds up being is this height right here. That forms the height of the rectangle. And so in continuing in this fashion, we summed all of these areas up in what's called a Riemann sum. And that looks something like this, where each height of each rectangle here is given by the orange quantity, which is just the function x squared evaluated at each point. So the first point would be 0, the next point would be x over n, the third point would be 2x over n, as an example, and x over n is giving the width of each rectangle or the length of each interval as we break this up into different segments. And when we took the limit of this expression as n goes to infinity, that would break this area up into infinitely many infinitesimal rectangles. You can see that as n goes to infinity, the width of each rectangle is going to become incredibly small. It will approach 0. And so when we broke that up into infinitely many infinitesimal rectangles, this Riemann approximation ceases to be an approximation and becomes a precise answer for the area under the curve. And what we found is that when we took this limit, we were actually able to evaluate this infinite sum, and we wound up reducing it to 1/3 x cubed. So in conclusion, what we found is that the area under the function x squared from 0 to some point x would evaluate to 1/3 x cubed. So what we need to do in this video is we need to introduce some new notation, and that's going to look like this. And this might look scary at first, but this is really just a way of expressing this idea of this infinite sum of infinitesimal rectangles. It's a way of distilling that into something that's honestly more simple, right? And so what this notation tells us is this funky looking S symbol here is called an integral. And this is telling us to take the area under the curve from the point 0 to the point x of the function x squared with respect to x. And we found that this is equal to 1/3 x cubed. And so another way of thinking of this is that this is really just the same thing as this Riemann sum. Here, this would be the function evaluated at each point, and this is the infinitesimal width of each rectangle. And this symbol here, another way to think about this is that this is just summing up all of those infinitesimal quantities. So each little infinitesimal segment of area that's given by one of these discrete but incredibly small rectangles summed up over the interval from 0 to x, that's going to give you the area under the curve of the function x squared from 0 to x. And what we found is that when we evaluated that was equal to 1/3 x cubed. So this notation is just a way of expressing the limit of these Riemann sums as n goes to infinity, and is a way to denote the precise answer for the area under the curve from some lower bound, which in this case is 0, to some upper bound x. Let's get some practice with this new notation by going back to these earlier examples, which were a lot easier to work with. So let's remind ourselves what this notation means. This is the area under the curve of the function y is equal to x with respect to x from 0 to some point x. So if we go along the x-axis x units, and we wind up at this arbitrary point here, and we draw an imaginary line, this is going to form some area bounded by the function and the x-axis. And what is that area going to be equal to? Well, this is just a triangle. the height of this triangle is going to be equal to x because it's just the function evaluated at this point, and that is just x. And the length of this rectangle, or the width of this triangle, the length of this triangle is going to be equal to x as well because that's how far along the x-axis we are. And so the area under this curve from 0 to x is just going to be equal to x squared over 2. That's just the formula for the triangle with a length and a base length of x and a height of x. And so we could write that here as our formula. X squared over 2 tells us the area under the curve y is equal to x with respect to x from 0 to some point x. And let's do the same thing for a constant. We want a function that tells us the area under the curve of some constant from 0 to x. And if we go along the x-axis x units here and we draw an imaginary line, this is just going to be some rectangle with a base length of x and a height of c. And so that's just going to be equal to c times x. And so here we have derived some formulas for these simpler cases of areas under curves that just form some basic geometric shapes. Now, one point that I want to make here with this new notation is that now we don't have to just take the area from 0 to x. I suppose we weren't limited to that in the beginning, but with that Riemann sum technique, it becomes a little bit more challenging to find the area over specific intervals. But what I'm noticing here is that if we want to find the area over some specific interval from a to b, instead of from 0 to some arbitrary endpoint x, we actually have the tools to do that. We could take this complete area here from 0 to b, for instance, which we already know how to compute, and we could subtract this area here, from 0 to a. The area from 0 to a here, or from 0 to b, I'll do that part first. The area from 0 to b of x dx, and we are subtracting a separate area, which is this orange area here, from 0 to a of x dx, and we know what these evaluate to. This is the same thing as plugging in, if you go back to this example here, if you plug in a value of a here, it's just going to be equal to a squared over 2. That would be the amount of area covered by this function. And so if we make those substitutions here, what we find is that the area from a to b of x with respect to x is just going to be equal to this giant area here, this complete area, which we found is just the area from 0 to b, which is b squared over 2, minus this smaller area in orange, which is a squared over 2. And what this is this is just that function that we determined to tell us the area under the curve from 0 to some arbitrary endpoint x, evaluated at the endpoint of that interval, minus that same function evaluated at the beginning of that interval. And because we're going to be doing this a lot, when trying to find the area under specific curves over specific intervals from some arbitrary endpoint, beginning point A to some arbitrary endpoint B, we actually have a notation for this. And the way that this looks, this is another example of new notation, and probably the last one in this course, is going to look something like this. We'll have our function, x squared over 2, and we're going to evaluate this function from x is equal to b to x is equal to a. And so what this notation means is exactly this. We are plugging in x is equal to b into this equation, into this function here, and then we're subtracting a being plugged into the same function. And so these are equal ways of expressing this idea. I do want to make one point here before I move on. Going back to this example here, now that we've established this new notation, this would not be correct. You can't have the same variable in these bounds here as you have right here. The only reason I didn't make this point earlier is because I was already introducing a new notation. I didn't want it to get overly confusing, but the correct way to write these different things would be the area from 0 to some endpoint x, and then you would have to use a different variable here. So for example, we could write u du, and that would be equal to, let's see here, the function u squared over 2. That would be the same thing here. We're just changing the variables. It's this triangular area here, and we would evaluate this from u is equal to x u is equal to x, u is equal to 0. And what that would evaluate to would be x squared over 2 minus 0 squared over 2, which is just x squared over 2. So this would be the correct way to write these. You cannot use the same variables here. Now that we've covered that new notation, what I want to do to end this video is come up with a function that allows us to determine the area under the curve sine of x over the length of some interval from 0, from the origin, to some arbitrary endpoint b. And in this case, I'm using the variable b as my limit of integration, which is what these parts of the integral are called. I'm using the variable b there to avoid a conflict of variables with the integrand, which is what this part of the integral is called. This part is called a differential. And so I want to see if we can find some function to give us this area with an arbitrary endpoint b so that we can plug in whatever we want. The reason I want to do that is twofold. Number one, the result of this problem is going to give us a hint as to how we can solve these sorts of problems much, much more easily. And also, I want to see if we can determine what the area under the function sine of x is over this course of this little hump here from 0 to pi, because the answer there is pretty interesting. So let's get started. So just as with the example of x squared, what I want to do is break up this area here. I want to break this up into several different minute rectangles of different areas. And I want to take the limit as the number of rectangles goes to infinity and their widths get smaller and smaller and smaller to the point where they are infinitesimal, and we're getting several little infinitesimal shreds of this area. And if we sum all of those up and we take the limit as the number of rectangles goes to infinity, that answer is going to cease to be an approximation for the area under the curve and is going to become a precise answer for the area under the curve. And so writing that out mathematically, this area here from 0 to b under the curve sine of x with respect to x is going to be equal to the limit as n goes to infinity, where n is representing the number of the rectangles that we're using to approximate this area. And we're going to sum up all of these different areas from the first one all the way to the nth one. And the area is going to be given by the function evaluated at the beginning of each interval. So in this case, I'm just going to do sine of, and for the first value here, it's just going to be 0. And then we're going to add incrementally to this. So it's going to increment by I, and then we want to multiply by the width of each rectangle in order to move to the next one. And the width of each rectangle will be the length of the interval divided by the number of rectangles. Length of this interval is just b, and we're dividing by n rectangles. So this is going to be the function evaluated first at 0, then at b over n, then at 2b over n, then at 3b over n, where b over n is just the width of each rectangle. So this here is going to give us the height of each rectangle. And now that we've sort of walked our way through that, we can erase this 0. It ceases to become necessary. That's just for intuition's sense. And so we can make this a little bit neater, move this over. And now we want to multiply by the width of each rectangle, which of course is just b over n, the length of that interval broken up to the number of rectangles. And now I want to negotiate the sum. The first thing I want to do is I'm going to pull this out of the sum, because it's going to depend on the limit, but it's not going to change. It's just a common factor as to all these different little heights. And so when we pull this out, we're going to get the limit as n goes to infinity of b over n times the sum from I is equal to 0 to n of sine I times b over n. Now, in order to deal with the sum, I'm first going to write it out, and I'll do this in a different color. This is just this part that we're dealing with right here. So this sum is going to be equal to, written out, this would first be sine of 0. This is going to be sine of 0. Then we're going to add sine of b over n here. Then we're going to add sine of the next value would be 2b over n, 2b over n. And then we can add sine of 3b over n, 3b over n. And this would continue all the way to our last value of sine of, let's see, we would have nb over n. Well, that's just sine of b. And so this is what our sum looks like written out. Now at this point in the story, we might be starting to feel a little bit lost. One of the primary reasons for this is because this series does not obviously converge, and indeed it's even less clear than the last video when we talked about the function y is equal to x squared. But I want to make the point here that this series is a factor in determining a very real physical quantity here, represented by the area under this curve, or a very real geometric quantity. And if this is a factor in determining something that is observable, some geometric quantity, then I would make the argument that that means that this series has to converge. And I'm going to give a little hint here, because I know that the series converges. I've already worked out the math. But if you want a chance to work it out on your own and to see what the series actually converges to, I made use of this trigonometric identity, which says sine of something times sine of something else is equal to 1/2 of cosine, that first thing, minus the second thing, minus cosine of the first thing plus the second thing. This is just a trigonometric identity. And my thought process was, here on one side of the equation, I have the value of the sum. And on the other side, I have the sum itself. And if I were to multiply both sides of the equation by the same thing, what I would get is just one quantity here, for example, sine of alpha. And then when I multiply the other side of the equation, I would have to distribute that along all of these different factors. So by multiplying both sides of this equation by sine of something, what I could do after that is I could break up each one of these things that I'm adding together. I could break up each one of those into this 1/2 cosine of the first thing minus the second minus cosine of the first thing plus the second. And if I was able to find some factor that allowed me to break this up and allowed for the fact that once broken up this first term, for example, once I broke that up into its cosine constituents after multiplying by some specific factor, if I could find a factor that allowed for the negative part of the first term to cancel with the positive part of the next term, if I could identify that factor, then I would be able to cause the middle of this entire series to cancel. Every single thing would cancel, because the negative of this would cancel with the positive of the next term. And then the negative of that term would cancel with the positive of the following term, etc. And what I would be left with is I would be left with this positive cosine value from the first term, which, since this is 0, would come from here. And I would be left with the negative cosine value from the last term. And then that would be a lot easier to evaluate than this completely infinite sum. And so that was my method. I'm going to give you a chance to pause the video and see if you could identify what that factor might be to allow for that convergence. So hopefully you paused the video and gave that a shot on your own. This is how I came up with an answer here. What I wanted is negative cosine of the term before. So I'll just call that the ith term. That would be, we know what one of these values has to be, and that's going to be IB over N. Here it's B over N, here it's 2B over N, here it's 3B over N. So that's a given. So we want that IB over N plus some factor, and here I'm just going to use the beta given by this identity. We want that this is equal to the negative, or that this is equal to the positive of the next term, which in this case would be our alpha, but for the next term, which is just going to be I plus 1 times B over N minus our factor here. And so now we can actually solve this to get what our factor needs to be. And so in doing that, what we would get is we would get that 2 times beta would equal I plus 1 times B over N minus I times B over N. And this is actually pretty simple. These i's are going to cancel. We're just left with 1B over N. And so this is just equal to B over N. And so the factor we need to multiply by on the inside here is going to equal B over 2N. And so if I multiply both sides of this equation by sine of B over 2N, what I should expect to see is a lot of cancellation with all of these middle terms. And so let's go ahead and carry that out and see what we get. So I'm going to rewrite that down here, and I'm also going to get rid of this sine of 0 term because that's just equal to 0. And so what I'm going to get down here, I'm going to multiply both sides by sine of b over 2n, and I'm going to multiply by the sum on this side, and then here on the other side I'm going to have to distribute this across everything, and I'm going to get rid of this sine of 0 term. So I'll get sine of b over n times sine of b over 2n. And for my next term, I'm going to get sine of 2b over n times sine of b over 2n. And then for my next term, I'm going to get sine of 3b over n times sine of b over 2n. And then for my last term, what am I going to have? Well, I'm going to have sine of b times sine of b over 2n. And so this is the last term. And so now what I can do is I can use this trigonometric identity in order to break these up. And so this one would become, let's see, I'm going to have a common factor of 1/2 across all of these things. So I'm just going to break that out. And then here what I'm going to get is I'm going to get cosine of the first thing inside the sine minus the second thing inside the sine. So b over n minus b over 2n, that's just equal to cosine of b over 2n. I'm going to have to subtract b over n plus b over 2n, which is 3b, cosine of 3b over 2n. And then if I did this correctly in identifying this factor that I need to multiply both sides of in order to get this cancellation, what I should notice is that the next positive cosine term of this factor right here, this positive cosine term should cancel with this one. And so that positive one is going to be cosine of 2b over n minus b over 2n. And 2b over n is just 4b over 2n. 4b over 2n minus b over 2n is 3b over 2n. And so I'm going to have to subtract here I'm going to add here cosine of 3b over 2n. And then I will subtract these two terms added together. And that's going to give me cosine of 5b over 2n. And as expected, these two will cancel. And then here, if you carry this out, what you'll notice is that the next term is going to be cosine of 5b over 2n. And so successfully we did this, and it's going to cancel with all of the middle terms. And the only thing we're going to be left with is this negative cosine of alpha plus beta, but for this last term here. And so what would that equal? Well, we would have a bunch of terms that cancel in the middle here, and then we would have minus cosine of b plus b over 2n. And so you would have to multiply b by 2n over 2n. We would get 2nb over 2n minus b over 2n. So it's just going to be minus b here. And because everything cancels here, what I have is that sine of b over 2n is equal to, or multiplied by the total value of the sum, is equal to 1/2 of cosine b over 2n minus, and then everything in the middle is going to cancel, and we're left with cosine of 2nb minus b, and that's just equal to 2nb, or 2n minus 1 times b. You can factor out that b, and it's going to be divided by 2n here. So factoring out the b, it's going to look something like this. And then if I want to find what the value of this sum is, I just have to divide both sides by sine of b over 2n. And so I get that the value of this sum is going to converge to 1 over 2 sine of b over 2n multiplied by cosine of b over 2n minus cosine of 2n minus 1 over 2n times b. And so we made a lot of progress here. We were able to reduce this sum down very nicely to an equation that looks awful, but is still a lot better than a completely infinite sum. And so we're not finished here, though. We haven't finished our mission, which, as a reminder, was to evaluate a function, or to come up with a function that gives us the area under the curve y is equal to sine of x from 0 to some arbitrary endpoint b. We determined that it must be equal to this infinite sum here, and we factored out our b over n, but we still have to take the limit as n goes to infinity and add in this factor of b over n, which represents the width of these rectangles. Once again, we finished this part. We just need to add this in, and we will have our answer for this, the area under that curve from 0 to some arbitrary endpoint b. And so let's carry out that operation. The only thing that we have left to do is we have the area from 0 to some arbitrary endpoint b under the curve sine of x with respect to x is going to equal the limit as n approaches infinity of b over n, and then we're going to multiply by this here because this is the value of that sum, this sum right here, this one. And so if we're going to multiply this, what I'm actually going to do here is I'm going to move this b over n, although it's going to look awkward at first. I'm going to put this b over n as the numerator in this fraction here, 2 times sine of b over 2n. And then I'm going to multiply by all of this, which I just have copied. That's the rest of that sum. And then what's going to happen as we take the limit as n goes to infinity here? Well, one thing that I want to point out is that here, this value inside of the sign is going to be extremely small. It's going to be infinitesimal. And I'm not sure if you remember, but in an earlier video, or maybe you didn't see it, we talked about linear approximation. And what we found is that for values of x that are extremely small, sine of x is approximately just equal to x for values that are very, very, very close to 0. And everything in here is going to be extremely close to 0, infinitesimal. And so that approximation actually becomes an accurate answer. And so that is to say, when we take the limit as n approaches infinity of this, sine of b over 2n is just going to become b over 2n. And when we multiply by the 2, it will become b over n. And so what this is going to reduce to is we'll have b over n in the numerator and b over n in the denominator, and this whole thing is just going to cancel nicely and be equal to 1. So that's good. And let's see what happens to the rest of this as we take the limit as n goes to infinity. Here, we're just going to have cosine of 0 if we take the limit as n goes to infinity. And cosine of 0 is very simple to evaluate, but I'm just going to leave it as cosine of 0 for now. This is equal to cosine of 0. And then here, what is going to happen if we take the limit of this expression as n goes to infinity? We have, well, as n goes to infinity, the difference between 2n minus 1 and 2n is going to become negligible. And this is also going to reduce to just 1. It will be, essentially, will just be 2n over n, or 2n over 2n, which is going to reduce to 1. And so what we're going to be left with here is we're going to subtract cosine of b. And this is actually our answer. We are done here. We have the area under the curve sine of x from 0 to b is equal to cosine of 0 minus cosine of b. Now, I'm going to rewrite this a different way. Obviously, cosine of 0 is equal to 1, so you could just rewrite this as 1 minus cosine of b. But the way I'm going to rewrite this is going to look strange at first, but this is actually equal to negative cosine of b minus negative cosine of 0. And you might be wondering why I would want to rewrite that in this manner. This allows us to use our earlier notation, which said that this is equal to, it's the exact same thing, but this is just rewriting this a different way. Negative cosine of x evaluated from x is equal to b, x is equal to 0. And so that's my final answer here. Now, as one final note here before we move on, one thing I want to do is I want to go back to this curve, and I want to see if we can figure out what the area is under one hump of the sine of x curve. So this area here, I want to see if we can calculate it given what we had just figured out. And so if we want to figure out the area that's bounded by the function sine of x with the x-axis from 0 to the next point where sine of x is equal to 0, which happens to be the point pi, what we want is the area from 0 to pi of sine of x dx, and we just figured out that that's equal to negative cosine of x evaluated from the upper bound, So x is equal to pi to the lower bound, x is equal to 0. And if we evaluate this, what we're going to get is negative cosine of pi minus negative cosine of 0. And you have to be careful here. Cosine of 0 is equal to 1, so this is going to be negative 1. And we're subtracting it, so we're going to add 1. And then here we have negative cosine of pi, and cosine of pi is negative 1. So negative negative 1 is positive 1. And so this area here is going to be equal to 2. And so I think that is pretty neat, that the area under this sine of x curve from just one of these humps is equal to 2 units squared. Pretty neat. And as a final note for this video here, I'm going to give us a hint as to how we might be able to deal with these situations in the future, because that was a whole lot of work to figure out what the area under that sine of x curve was equal to. We had to deal with that gigantic infinite sum. It took a lot of thinking, trying to figure out what factor I could use to get that sum to converge. But here, I want to notice a pattern, which is that if we want to find the area under the curve of a constant, what we have to do is just take that constant multiplied by x, evaluated at the upper bound minus the lower bound. If we want to take the area under the function x, we have to take the function x squared over 2, evaluated at the upper bound minus it evaluated at the lower bound. If we want to do the same for x squared, it's x cubed over 3, evaluated at the upper bound minus it evaluated at the lower bound. If we want to do the same for sine of x, we have to take negative cosine of x, evaluated at the upper bound minus the negative cosine of x, evaluated at the lower bound. I want you to pause and ask yourself if you notice a pattern here. It seems to me that this function here, whatever you're seeing in the integrand, winds up being the derivative of the function that we need to evaluate at the upper bound and the lower bound. If you took the derivative of this function, negative cosine of x, the derivative of cosine of x is negative sine of x. So the derivative of negative cosine of x is sine of x. That's what we have here. The derivative of x cubed over 3 is equal to, well, 3 times x squared divided by 3, x squared. That's what we have here. The derivative of x squared over 2 winds up being equal to x. The derivative of a constant multiplied by x winds up being equal to that constant. And so we're starting to see a connection here, where if you want to take the area under that curve, you just have to find a function that when you take its derivative is equal to the function where you're trying to find the area under its curve. And so here we're seeing a clue as to, 1, a connection between these derivatives and the areas under the curves, and 2, a reason why we might want to work backwards and take what's called an antiderivative, which is going to do the opposite of what a derivative does. It's going to find a function whose derivative is equal to the function that you're dealing with. If I wanted to take the antiderivative of x, the antiderivative of this, that would give me x squared over 2. Because when I took the derivative of x squared over 2, I would be left with x. And so in the next video, we're going to go explore this topic a little bit further. We're going to talk about antiderivatives, and we're going to finally talk about the Fundamental Theorem of Calculus. Funnily enough, towards the end of the course. But that's what we're going to do for the next video. Thank you guys for watching. I'll see you then.